Good evening and welcome to Everything Matters, Tales from the Periodic Table, and to the Canbar Forum. Not our usual venue for doing this. We hope you enjoy this. It's a wonderful room that we have here. We've made it up to element number 14, silicon, and so this is kind of one of my personally favorite elements here. I'm in my element tonight because I'm kind of a geek, so silicon obviously is really important to me. I hope you all got your collectible card. Do you all have your collectible card? Excellent, okay. This card tonight is kind of really special. This was designed by one of our web folks, Rob Rothfarb, and this is your magical key to the world of augmented reality. If you take out your phone and you download, there's an app called Layar, L-A-Y-A-R, and I have it running here on my phone. There we go. And I think we can get a shot of it from here. Maybe we can even put it up on the screen, I don't know. Can we get that shot up on the screen? Maybe. We didn't rehearse that part, did we? Oh well. And you show the phone the card, you'll get a three-dimensional radiolarian. Am I right there, Denise?
Yes, that's true.
Radiolarian, hoo-hoo.
It's related to a radiolarian.
Floating in 3 dimensions above the card itself, and as you change the perspective on the card, you can actually look around the 3D object, so it's actually really cool. Take that home and try it at home. Download the app. It's free. And this will work across platforms, so you can do it on your iPhone or your Android phone. So we have a new thing. It's very cool. Oh, you got it up? Did you see it up there? Okay, great. Okay. I do not want to install software updates. Okay. There's other cards. I think if you missed a few of our Everything Matters Tales from the Periodic Table, I set up to element 14, so you can actually go outside, and I think we have them starting at hydrogen, element 1 out there, so you can make up for the fact that you didn't come to all the other talks. But we hope you'll come back and repeat these when you get here. How many people have cards from previous talks? George does. Patio does. Okay, well, you have the chance now to complete the collection. There will be 118 cards in this collection by the time we finish. I'll be in my 70s. It'll be a long time from now. Now, I'm just the first speaker. I'm Ron Hipschman, your host for this series. And I'm going to be followed by Denise King. Denise, who's sitting over there. She is an Exploratorium exhibit developer. And I'm going to read so I don't miss anything here because there's a lot of stuff that Denise has done. She's studied subjects ranging from botany and ecology to marine biology, microbiology, and evolution. She worked previously as a field biologist and a lecturer at San Francisco State. Hey, so did I. Different departments probably. And once got to shoot on location with English broadcaster and naturalist David Attenborough in the Mojave Desert. That must have been fun. And so she's going to speak directly after me, so we won't take a break, we're just going to run right into each other here. And so I'm just going to start right now, and we're going to start talking about silicon. Let's bring up the old periodic table. Everyone should be familiar with this by now, if you've attended a few of the talks. Silicon, we start up here with hydrogen and helium, and we're running down the rows here, and we finally have made it down to silicon right there. So tonight, silicon is our subject. It's the 14th element, and that means it has 14 protons in its nucleus. Different numbers of neutrons, we'll get to that. It's in the column of the periodic table that we call the carbon group because it's headed up at the top by carbon. It contains a lot of very interesting elements in it that have interesting electron configurations that allow them to be used in a lot of interesting technology, actually, that we'll talk about. Silicon. The name actually comes from a word silicium, which is Latin for silex, hard stone or flint. Because if you actually look at silicon itself, here's a chunk of silicon. Here I have a couple chunks of silicon here. Why don't I just start them around the room so you can actually feel silicon. Silicon is actually a very glassy, hard. It doesn't feel like metal. It breaks like glass. It's not too heavy. It doesn't feel like metal in its density, and we'll talk about that as well. The first person to actually think about silicon was Antoine Lavoisier, and he didn't know about the element himself, but he looked at sand, at silica, and he said that looks like it's an oxide of something, but he didn't know what it was an oxide of. But he was the first guy to kind of think about that. Then we have to move on to Sir Humphrey Davy, who actually has a place in every single Everything Matters Tales from the Periodic Table talk I've ever given, because he actually discovered an awful lot of elements. And he's proposed that the silicon, oops, sorry, I just unplugged my laptop. That silicon, he thought the silicon was actually a metal. And so he's the one that gave it the IUM, silicium ending. The IUM endings are mainly metals. It's not aluminum, aluminium, chromium, and all of those elements have an IUM ending, because he thought that this was going to be a metallic element. He was wrong. This guy here, Thomas Thomson, he gave it an ON ending, because those are kind of the non-metallic elements, so like carbon and boron, and so silicon, and that's the one that actually stuck. The first guy to actually purify silicon was this guy, Berzelius, and he first purified a powder of silicon, and it actually kind of looked like a brownish powder in what he got. It wasn't a very pure sample. What you have in your hands there is extremely pure silicon. What you have in your hands is also, it's a polycrystalline. It's not a single crystal, and we'll talk a little bit about that later. Silicon's pretty common. Here is the periodic table with the elements sized as if the size of the element was its abundance, and you can see that silicon right here is actually pretty abundant. It's got a pretty large square. When we finally get down into some of the transition elements, then we get down to some pretty rare stuff down here. If we kind of look at the abundances, you can see in the universe, silicon right there is about the 8th most abundant element in the universe. It actually forms about 0.07% of the universe. Not a lot, but still a good percentage. It's the 8th most common. And it's about the same in the sun. If we look at the sun, it's about the same, because you would expect that, because the sun is kind of made out of the same stuff that the universe is made out of. It's about 0.09% of the sun's composition. But now we start looking at things like meteorites, which are solid. They're not gaseous bodies like the sun. If we start looking at solid bodies like meteorites, it's the 3rd most common thing in meteorites. Most meteorites are actually silicate in nature. They're stones. They're not metal. They're actually kind of rocks. And so it's the 3rd most abundant thing in meteorites, right behind iron. But if we look at the crust of the Earth, now we get to something very interesting. It's extremely abundant in the Earth's crust. It's the 2nd most abundant element in the Earth's crust, just after oxygen. And if we again look at the oceans, it's not quite as abundant in the oceans because it's not a real soluble kind of mineral. And in the human body, it's not a very important component either. It does form some parts of like collagen in your body, so there's some important things it does. There's lots of different forms of silicon. We talk about isotopes, and isotopes are different forms of the same thing, isotope. And there are a lot of isotopes of silicon. The only difference between these silicons, they all have 14 protons in the nucleus. They have different numbers of neutrons. You add protons plus neutrons and you get that number right there. So there's a lot of them. Most of these are radioactive. They're not stable. They don't exist on the Earth. There's only 3 stable forms of silicon. And it's silicon-28, silicon-29, and silicon-30. So this silicon here has 14 protons and 14 neutrons. This has 14 protons and 15 neutrons, 14 protons and 16 neutrons. And those occur all in nature, but they have different abundances because of the way they're made. So if we look at the abundances of this silicon, you notice that the silicon-28 is 92% of all the natural silicon, with silicon-29 being 4% and silicon-30 being about 3%. So most of the silicon that you have in your hands now, wherever it has gotten to, is silicon-28. As you can weigh that silicon in your hands, it's actually not super dense. 2 grams, 2.3 grams per cubic centimeter. Remember what water was? 1. Right. So it's about a little more than twice as dense as water. Not really very dense, especially if you compare it to some of the other things in the table, like iron, which is 7.8 grams per cubic centimeter. gold, which is 19 grams per cubic centimeter, and the heaviest element, which is 22 grams per cubic centimeter. And if you want, I have another chart here. Let me just set it off. Tungsten's way up there, very, very dense. Lead and iron and aluminum, magnesium, and silicon's right between aluminum and magnesium, right there. And so it's a fairly low density element. So you can try, if you want, come up after, and I have a few, well, some of these aren't elements like maple and plastic, but I gave them chemical symbols anyway. But you can try magnesium, aluminum, copper, iron, and lead. Feel the density differences. I forgot to bring the tungsten with me. So compounds of silicon, the most common one that we find is quartz in the crust of the Earth, silicon dioxide. Beautiful, forms these beautiful crystals that you find at various psychic fairs. But I like them just because they're really beautiful crystals. I've never found them to cure me of anything. They can be formed quite large too. Silicon dioxide is what makes up sand on the beach. Most sand. The black sand is a different thing. That's iron oxide, and we'll get to that when we get to iron. There's another element on the Earth that's actually another mineral on the Earth that's quite common, olivine, probably named for its color, I suspect, peridot, semi-precious gem. This actually occurs in meteorites. If you look at stony iron meteorites, here's a stony iron meteorite. See, the iron is all this silvery stuff, and look at the stony part here. Look at that same yellowish, greenish stuff. That's all olivine. This is a really kind of rare form of meteorite. This one is actually owned by the California Academy of Sciences. They let me borrow it so I could scan it, and it's a beautiful piece, beautiful specimen though. I'd love for you to be able to see this live, but I don't have it here with me. Stony meteorites, which are all silicate mainly, look like this. You would hardly tell them from any other form of rock, except if you look really closely, you'd notice little glass spheres in them. Those little spheres are called chondrules, and so these are called chondrites, these kind of meteorites. And this is the most common form of meteorite. You would not kind of see it if it landed on the ground. You probably wouldn't notice the difference between that and a rock. The iron meteorites, which are either all iron or iron plus the olivine, you kick those and you hurt your foot. So you notice those. So those are even though these are the most common, the iron ones are the ones that you see most of the time in the museums. So where do we get silicon from? Here's the periodic table with all how they're made, and you look here at silicon, you see it has a dollar sign and an L there. That means it's made in supernovae or very large stars. So small stars don't make silicon. You have to have a big star that can have a lot of gravity, very hot center at the time of its death. It's made in a process called oxygen burning, don't you use oxygen to burn? Well, you can burn oxygen too. So you start off with an oxygen, you add to it, yes, more oxygen. And the result of that reaction is silicon. But I hear you say, but 16 plus 16 does not equal 28, and 8 plus 8 does not equal 14. Well, you get something else out of this reaction as well. You get helium. So that adds up. So that's the oxygen burning reaction that happens. And this all happens in stars that are very, very hot. The stars are like I have to look at my notes here because I can't memorize this stuff. Between 1.5 and 2.5 billion degrees at the center of the star. These are very large stars with a lot of pressure, squeezes that stuff really tightly together. As a matter of fact, the matter that's fusing and doing this oxygen burning is at a density of about 2.6 to 6.7 billion grams per cubic centimeter. That's pretty dense. If I had a cube of that in my hand, well, I couldn't. It would drop through my hand, it would drop through the floor, it would drop through the earth, it would actually sort of go into orbit around the center of the earth, just flying through solid rock. It's so dense. But that's not the end of the process. Silicon burns too. If the star is large enough and there's enough gravity to heat the center of the star up, you can get silicon burning. So silicon burning starts by adding a helium to it, which gives you sulfur. That's not the end of the story. By the way, that oxygen burning all happens within 3 days, the last 3 days of the star's life. This process takes about 1 day. So silicon, you add helium to it, and you get sulfur. Then you take that sulfur and you add helium to it and you get argon. And you take argon, you add helium to it and you get calcium. You take calcium, you add helium to it, you get titanium. You take titanium, you add helium to it and you get chromium. And finally, you take the chromium and you add helium to it and you get iron. And that's where everything ends. Because to make iron fuse, you have to put in more energy than you get out. So there's no more source of energy at the middle of the star collapses, it forms a supernova, and at the center of that supernova you get a black hole or a neutron star. So silicon burning happens just at the very last stage of the star's lifetime, only about a day's worth of burning. So the silicon atom is actually pretty big compared to the hydrogen atom because it has electrons hanging out on the outside. And speaking of those electrons, let's take a look at that. So here's kind of the electron configuration of silicon, except there's 4 electrons in the outer shell here, which leaves 4 spaces for electrons. So silicon would like to either get rid of 4 electrons or like to inherit 4 electrons. So it would look like a noble gas. In chemical reactions, it has a valence of 4. And so we'll see how that joins together with other molecules in just a bit. I just want to just quickly look at the spectrum, which is interesting, but nothing totally distinguished. It's hard to see anything in the sun spectrum that shows you silicon. But I wanted to now talk just really quickly about some of the other compounds that silicon makes, because this is very important, because this is one of those things that grates on me. Silicon is not silicone. Okay? They're different. Silicone is a polymer. It's a chain, indeed, of silicon atoms joined with oxygen atoms, long chains. It's useful. It's a hugely useful substance in industry. You've encountered it probably in this form right here, this caulk that you use for bathtubs or for aquariums. It's rubbery. It kind of dries in about a day to this wonderful rubbery substance that sticks to everything. However, there are forms of silicone that don't stick to everything. For instance, this is my pie cake silicone mold. Pie, yeah, it's not a pie, it's a pie cake mold. This is for Pi Day. You should come on Pi Day, March 14th, 314, come on Pi Day. So that's a non-stick silicone mold. I put this on my windshields of my car. This is a silicone substance as well, Rain-X, and it has a little tail. On the tail end of that long chain, there's something that doesn't like water, and so it repels water. It's hydrophobic. So that's another useful silicone substance. We're all familiar with this use of silicone, of course, implants. They don't actually use, I don't think, silicone implants anymore. They now use saline implants, which are really kind of a bag of water, of salt water, because it's innocuous inside the body, whereas the silicone can allegedly cause some problems. That feels like a bag of salt water, but I read an article on this online, that's where I got the picture. They described this as feeling like a gummy bear, okay? An important silicon substance is Portland cement, because it's used everywhere, man. It's used in concrete and mortar and stucco and grout. This is used industrially, worldwide, and in huge quantities. We're all familiar with silicon dioxide in the form of porcelain or in the forms of clays. So silicon is a semiconductor. Now we're going to talk about the really interesting stuff with silicon, for me anyway. A semiconductor. A semiconductor. Is that like being flammable or inflammable or non-flammable? Sort of, because it's less conductive than a metal, a conductor. It's more conductive than an insulator. It's kind of in between. It has some interesting properties. It changes resistance with light exposure, which means it's useful for detecting light, or maybe even gathering light and changing its form from light to electricity. This is really interesting. Most things, when you heat them up, their resistance to electrical flow increases. So tungsten filaments, if you put electricity through them, they get hotter, and it's harder to push electricity through them. Silicon's not like that. It actually lowers its electrical resistance as it gets warmer. It doesn't make good filaments because they burn out immediately if they're like that. And last but not least, you can make silicon, which is normally a pretty good insulator, more conductive by introducing into it a small impurity of another substance. And that's going to be very important. We're going to talk a little bit more about that. They call that doping. There's other semiconductors other than silicon, boron and germanium, arsenic, antimony and tellurium. Those are kind of the main ones. There's some on either sides of that some people might consider weak semiconductors, and some of these others like boron and phosphorus are used to dope silicon to make it more conductive. On our roof, we have a really great example of an application of silicon, which is silicon solar cells. Our roof, we have 5,874 solar panels made by SunPower over across the bay, and we are trying very hard to be net zero. So we are trying to generate as much electricity as we use, and that's our goal. We're very close to it right now. We're almost there. As we learn how to use the building and we learn how to use electricity here, we're getting better and better and better at it, and our goal is to use no electricity net from the grid. Obviously, right now we're using electricity from PG&E because it's night and we're not generating any, but during the day we actually generate more and feed it back to PG&E. These are solars. Here's a different kind of solar cell. This is not a SunPower solar cell, but I'm going to give you guys a challenge. This is like paper thin, but glass-like. I'm going to pass it around. If you break it, it's okay. This is an amorphous solar cell. You can see the crystals of lots of crystals in that underneath the blue layer.
Looks like
Polycrystalline. I doubt you guys can pass this around without breaking it. It is so thin and so delicate. This is your challenge for the evening. So how about putting silicon together? You can make really useful devices out of silicon. It has 4 electrons that want either to get away or to join other atoms, and it has 4 holes that it wants to fill with electrons. And so it joins together, like carbon, in double bonds, like this. And if you look at it in a little larger scale, it forms can form a large crystal like that. The interesting thing here is if I hook a battery to this and put the wires to each end of this piece of silicon, no current will flow. It's a very good insulator. But I can make it a better conductor, less of an insulator, by doping it. I can add some atoms to it that are some impurities. And I mentioned already, phosphorus is one of those. And it's the element that we're going to be doing in October. We're going to take a break. I forgot to mention this at the beginning. We're taking a break with Everything Matters, and we're coming back with phosphorus in October. So phosphorus has 5 electrons available to it. So it has kind of one more than silicon. So if you take phosphorus and you dope the silicon with phosphorus, now you have a bunch of little electrons, negative things, that are available to conduct electricity. There's extra negative things hanging out there. So this is negative. This is called an N-type semiconductor, N. And if you hook a battery to this and connect it up, because of those impurities, these electrons are available to allow the electricity to flow and you get a current. Likewise, you could add boron to it. Boron has 1 too few electrons. When you put that in there, let's dope it. There we go. Now there's actually little positive centers right here. There's only 1 electron, and it really wants to have 2 there. Wants to have 2 there, wants to have 2 there, and so on. So this is kind of like a positive. It's an anti-electron. It's a hole. They're actually called electron holes right there. And actually, if you hook up a battery to this, that's called a P-type semiconductor, and if you hook a battery up to this, because it's positive holes, you hook a battery, current will flow. You've made it conductive by adding that impurity to it. The really interesting thing happens when you have both together. So you take a piece of P and a piece of N, you slam them together, and what happens? So the positives and the negatives are right next to each other. They attract. And so some of the positives get attracted over into the negatives, some of the negatives get attracted over into the positives, they cancel out, and that creates a neutral zone. If you're a Star Trek person, you know what I'm talking about. It's actually not called a neutral zone. It's actually called a depletion zone, where it's actually kind of like an insulator again. It's like it's not doped there. And so if you hooked a battery up to this, depending on how you hooked up the battery, different things will happen. If you hook the battery up this way, so the positive is connected to the negative side, the positive battery lead attracts the negatives here. The negative side of the battery attracts the positives here. What happens? Well, let's watch. So there's, see the negatives went over there, and then watch the positives right here. They get attracted closer to the negative side of the battery. What does that do? It increases the size of the depletion zone, and no current will flow. What happens if we take the battery and switch it around? Let's hook the positive side on my side of the screen here. There we go. And let's hook it up. Now, if we look what's going to happen, the positive side of the battery here is going to repel the positives here in that direction. The negative side is going to repel the negatives. Let's watch it happen. There's the positives getting repelled into the depletion region, and the negatives getting repelled into the depletion zone. That reduces the size of the depletion zone, and current flows. So this is a device that if you hook it up in one direction, current will flow, and if you hook it up in the other direction, no current will flow. This is called a diode. So it's a really cool electronic device made with silicon, N-type and P-type silicon. Now there's one more device that's even more useful, and I'm not going to really explain how it works. It looks like this. It's where you take a piece of N, a piece of P, and a piece of N. It's called an NPN, but this is a transistor. What happens here is electricity can flow, electrons can flow from the negative terminal to the positive terminal, but only if you put a little charge here. The charge, the current that you put into this thing here will allow or not allow current to flow through that. So this can be used either as a switch, or if you raise the voltage a little bit, or raise the current a little bit, a lot of current will flow over here. So you can use it as an amplifier as well. So this little device is called, this is an NPN transistor because you have N, P, and N. Believe it or not, there are PNP transistors as well. Just different arrangement. They're just as useful. This can be used is the fundamental device in all the electronics that we use. Here's what it actually looks like in a manufactured device. It's a chunk of silicon, and the way they make it is they etch out this whole thing here, and then they deposit the P-type semiconductor in there, then they etch it out and deposit the N inside of that, and then they just put electrical connections on it. And you have things called the emitter, base, and collector. We don't worry about that. That's what it actually looks like in the circuitry that we actually have. It's easy to manufacture. You just have to etch and deposit, etch and deposit. The electronic symbol for it looks like this: collector, base, emitter. This is the thing that you vary to vary the current through this direction here. This is the small variation makes a big variation. The first transistors were made at Texas Instruments. At Bell Labs, but they were first manufactured by Texas Instruments. And these are some of the first Texas Instruments transistors. You can see in 1954, so there were no transistor radios before 1954. They were tubes. The first time that someone took multiple components and put them on one chunk of one substrate was this guy, Jack Kilby, and he was at Texas Instruments, and he put several transistors on one slide. Here it is. This is the first integrated circuit. Science is not pretty. This is the first integrated circuit. He got the Nobel Prize for that. Now that's a very simple integrated circuit, but notice there's components over here and there's a component right here. It wasn't all on one piece of silicon. The first guy to do that was down at Intel. Well, actually, he wasn't at Intel yet. Robert Noyce. He was actually, I think, at Fairchild when they did this. Then he went and founded Intel. And this is the very first integrated circuit that's on a single piece of silicon. That's called a monolithic integrated circuit. And that's really the basis for everything that we use, everything we have now, really, the monolithic integrated circuit. And they're built on wafers. So this is a wafer, And the first wafers that they used for integrated circuits, Intel used to build memory, they're carved out of these ingots of silicon. Actually, here's the end of one of those ingots right here that I thank you, Intel. If there's any folks from Intel here, they loaned me this end of this ingot. These very pure silicon, made as very pure silicon before they dope it. You can look at you don't find things with 1, 2, 3, 4, 5, 6, 7 nines after the 99. That's extremely pure. This is actually down in the Intel Museum. You can go and hug that if you want. That's about 15 inches in diameter and it weighs about 250 pounds. It's a giant ingot. Sorry, I have nothing here for scale. But this is the current type of ingot that they actually make wafers out of. They didn't start this big. They started with 2-inch wafers in 1969, and then over the years, the wafers got larger, became 4-inch wafers. There's a 4-inch silicon wafer, got a little larger. Here's an 8-inch silicon wafer. This one actually has some chips on it. And then eventually, today, this is the wafer of today, this wafer is actually 12 inches in diameter. Here is a 12-inch diameter wafer. Can I see all the pretty reflections in it? This actually has chips on it. This has Intel's latest Cherry Trail 14 nanometer second generation tri-gate transistors. So this is actually the current production so you should definitely come up and check this out. It's really quite lovely. But then these are taken and sliced. They slice this and dice it with a laser. And so you end up with chips, and those chips are put into a package. Here's a chip package right here. This is another Intel processor. This came out of a server that I retired. Well, at least it's retired now. This is and inside this is a processor. This is actually not a processor. I can tell by looking at it. This is a memory chip. This is probably something called an EEPROM, which actually you can erase by shining ultraviolet at it through a window. But you can see that it's connected to the outside world through a bunch of gold wires. And there's actually a lot more connections on this chip. There's probably a couple hundred connections on the back of this chip to connect the processor. Memory is a little bit easier to connect up. So I wanted to briefly talk about memory because I just had I've used memory for a long time. My first computer was an MSI, and this was one of the memory boards. Here, so you get a size on it. This is the memory board that was from my first computer. This is, are you ready for this? This is, well, you can see, this is a 4K, I said K, kilobyte memory card, 4 kilobytes, okay? This cost about $100 back in 1976. Seems like reasonable price for 4 kilobytes of RAM. This computer right here on the table has 16 gigabytes or gigabytes of RAM. $100. How much should the memory in this computer cost? The memory in this computer should cost about $500 million at this rate. $500 million. These little memory sticks, these are actually, I took this out of someone's computer today. A gig of RAM, that's a gig of RAM. $60 million worth of RAM right there. It's amazing. By the way, if the RAM in this computer was still this size, it would take up about a two-story house, 3,300 square foot house. And it would require, to power it, would require the 16 gigs of RAM would require 168 megawatts. That's what this required. So things have gotten a lot better over the years since 1976. So just to say thank you, Silicon.